right, so now let's talk about bounce diagrams, which is basically just kind of a way to formally visualize this back and forth propagation effect, but for the more general case of a bunch of mismatches between the generator and the load. So to introduce the concept, we're going to re-explore or re-examine one of the cases we already did, and that was the open circuit. Okay, so we'll draw the simple model here. We have the switch, and this just sort of goes down, and then there's an open circuit on the end. So we're going to call that Z naught and Z naught. So we're going to look at this circuit again, but we're going to explore it from the perspective of a bounce diagram. So we already saw that kind of time domain visualization of it over here. Excuse me. This guy here. You can imagine these snapshots of voltage on the line in your mind. And the bounce diagram is just kind of an interesting way to visualize this stuff in a slightly different formality. So what you do is you just essentially imagine a kind of space-time diagram where you just have time on one axis and space on another. So I'm going to call this 0, negative L. And this up here is going to be time. And what you do is it really helps to use a ruler here for some of this. So you imagine this is the generator, and now this is the load. And that voltage, that signal, is going to propagate down at the phase velocity. So we're going to do something like the following. So this is what it looks like for the positive pulse. I'm going to write this as Vg over 2, or a half a volt, like so. So this is space z, time on this axis. Okay? And you imagine that positive pulse going down this way. And this moment in time will be L divided by the phase velocity. Okay, because remember, L, distance, is equal to velocity times time, delta t. So that little delta t from here to here is just L divided by the phase velocity there. Okay, so that is the height. And then when it strikes the right boundary again, you get a reflected wave that goes back like the following. And that reflection also has an amplitude of 0.5 volts until it strikes the load, and then nothing else happens ever again on this particular line. So 2L over the phase velocity. So this is a bounce diagram representation of the open circuited load with some matches between the generator and the line. All right, just a simple sort of graphical representation for the circuit. And the real advantage of a bounce diagram is that if I start adding mismatches between both ends, you can imagine waves just sort of continually bouncing back and forth forever until they finally asymptotically approach some steady state solution. And so that is the beauty of the bounce diagram. So we're going to work through a special little case. This is simply straight from the book to help give you a sense of what the bounce diagram is doing. So we're going to redraw our circuit like so. So we still have that switch. And there's going to be a transmission line out to here with some loads. I'm going to call this Z naught, Z sub L, and this is Z sub G, V sub G, like so. So to do a nice generic example, let's mismatch everything. So again, this is in your book, where I'm going to say Z sub G is going to be 50 ohms. That's my generator impedance. My characteristic impedance will be 100 ohms. And then I have my load impedance here. Z sub L is equal to 200 ohms. Like so. Okay, so I've mismatched all three parameters. And just to give some extra grounding, let's say Vg is equal to 12 volts. So my generator has some actual voltage here of 12 volts. So what will the bounce diagram look like for this? So the idea is you close the switch and a signal is going to propagate down. There's going to be that voltage division effect right here from the start. Then it's going to strike the load and reflect, and then it's going to hit the generator again and see another mismatch and bounce back again, and then again and again, forever and ever and ever, until finally approaching some stable solution. So the bounce diagram is just a nice handy tool to help us visualize that little process. So let's give ourselves a nice, big, giant bit of room here. We'll do this. Okay, and then we'll come back over here. I hope I can fit all of this into there we go. Yeah, that'll just barely fit. Like so. Then we imagine here. So here is negative L. Here is 0. This is space Z. So that, remember, that's a little z, not a capital. So that's not an impedance. It's a distance. I'll call that space here. So I'm sorry, it's very hard to write a capital versus a little z sometimes with your hand. So be careful not to make that confusion. And then this is, of course, time going this way. Okay, so first things first, what is the amplitude of the voltage as it transmits from the generator into the line for that initial bounce? So what you do is you imagine that first bounce. You can draw a line going from left to right like the following here. So remember, this time here, delta t, is simply L over the phase velocity there, just like we did last time. So you can imagine the slope of this has a little bit of representation as well. But what we care about is what is the amplitude of that signal there. So again, you close the switch and there's a forward propagating wave. So let's sort of write this over here. I'm going to write this as V1 plus. So the first forward propagating pulse is going to be a voltage division between my generator and my impedance, because nothing over here should affect anything yet. So that will be V sub G times Z naught divided by Z naught plus ZG. That's the voltage divider equation. And what you'll get in this particular example using these values is 8 volts. So that's the amplitude of my forward propagating wave. So I'm going to write that down here, 8 volts. So that's the amplitude of the wave propagating to the right. Then that wave sees the mismatch at the load here, and it's going to reflect back. So what we'll do is we'll just draw that out. 3, 4, 5. So it helps to have a ruler for this, makes it a little easier. So now I have to ask, what is the amplitude of that reflected wave? So we come back here, I'm going to say V1 minus, so the first pulse going now to the left is going to be V1 plus times gamma sub L. So probably the book uses a little lowercase l. I'm going to call this a capital L, just to be a little more explicit. V1 plus times gamma sub L. So it's the reflection coefficient between the transmission line and the load, which is in contrast with the reflection that will happen between the generator and the line. So remember, let's find another little space somewhere here. I'm going to write this up here just for reference. Gamma sub L is equal to ZL minus Z naught over ZL plus Z naught. Just kind of in the back of your head. That equation should be burned into your memory by now. But I also have a generator reflection that's going to happen for the reverse propagating wave. And it satisfies the same basic form. So I'm going to call that ZG minus Z naught over ZG plus Z naught. So you use these values, and what you'll get is actually a value of 1/3. So I get 8 over 3 volts. That's for the right side. The left side will have a value of negative 1/3. But we'll worry about that. So what you come back here. So now we go back to our bounce diagram. This is the forward propagating wave, and then this is the reverse propagating wave. So it has an amplitude of 8 over 3 volts, whatever that fraction evaluates to, a little over 2.66. Okay, and then we have another wave that's going to propagate back. So let's draw this again. So what is the amplitude on this third reflection over here? So now I'm going to come back to my list. Sorry if I can't quite get everything in the same field of view. So V2 plus, so this is the second forward propagating wave. It's just going to be V1 minus times the reflection coefficient at the generator. Again, if you plug in these values, you get negative 1/3. So I'm going to get negative 1/3 times this guy here, 8 over 3 volts, which is negative 8 over 9 volts. So you put that back in over here, 8/9 negative volts. So you can probably see the pattern that's happening now here. So count this out. I have another wave here, 2, 3, and then this is going to propagate over. And so just bouncing on forever and ever, this will then be negative 8/27 volts, and then you'll get plus 8/27 times 3, which I can't do in my head. And then you get another, and this just keeps going on forever and ever. And so you notice the amplitude of these is getting less and less and less with each little bounce. And the idea is at any given moment in time, there will be some voltage as a function of z comma t. And you just imagine a vertical bar, say over here. Okay, so if you pick out some moment t sub 0 here, the total voltage at that particular location will be the summation of these simple little values. So if I pick out, say, t sub 0, I will get 8 volts plus 8/3 volts plus negative 8/9 volts, like so. And you can see as I go to infinity, I'll get like this infinite converging series. Okay, and that is the essence of a bounce diagram. So the higher up I go, eventually I start accumulating more and more little pulses, and I just start adding more and more terms as time goes on. Okay, so that is the essence of a bounce diagram. It's a nice way to just visualize this back and forth propagation of these waves, and it gives you some nice handy rules for calculating the voltage everywhere at a particular moment in time as this summation of all these forward and reverse propagating pulses. And so bounce diagrams in a nutshell.